Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad that you've taken the time to join us as we look at our topic today regarding measuring dynamic torque. And so as we go ahead and jump into the presentation, we want to talk about the value of measuring torque. And so obviously we want the tools that we are using that are providing torque to our components. We want those tools to be producing the correct and accurate torque. And so a 5-cent fastener that's not torqued correctly, if it's over torqued, that could put the fastener to the yield point, and any vibration on that can cause that fastener to fail and break. If the fastener is not tightened completely, the vibration in that can cause the fastener to loosen and we have failure again. So we want to make sure that we're getting the correct and proper torque in the assembly process. Well, that's what we are doing. And so with that, we want to take a look at how we can measure the different types of torque. We're primarily focusing right now on the dynamic torque, but you may hear the term static torque. And so the difference between static torque and dynamic torque, there are a couple of different definitions, but for our purpose today, static torque is going to be more related to a reaction that happens on a torque analyzer, for example, would be a static torque because there's no movement to the sensor or to the transducer. And so the opposite of that would be our dynamic torque. And so we're actually measuring something that is moving. And so that was going to be kind of the definition that we're going to be using for today's presentation. So when we're looking at tools that are moving, we do have hand tools, obviously, that are being used in the production environment, and those are moving and providing a dynamic torque to the operation. However, they do not pose as much of variation and variables that you may see with a power tool. And so as we can measure dynamically what's happening to a fastener with a power tool, that's going to give us a great deal of visibility on what's happening with that particular joint, because there are a lot of variables, again, that can present themselves when we're looking at a dynamic type of rundown. So you could have influence from thread locker that now is acting as a lubricant. You could have different types of gaskets and washers. Is the fastener cutting something? So all of those different variables can play into the joint characteristics of the dynamic application for the particular joint that is being used. And so we want to be able to test that and see how we can be setting up our tools correctly to help compensate for those different variables within the process. And so when we want to look at measuring dynamic torque, how can we do that? There are a couple different ways, but we're going to primarily look today at the use of a rotary torque sensor. And so what is a rotary torque sensor? Well, this is a device that we can go ahead and we can pair it with a torque analyzer. Then we can put the tool the analyzer sensor between the tool and our part. And this will allow us to dynamically test what's happening on the joint as it's being run down. And so this can be used again with either a power tool, electric shutoff tool, could be a pneumatic shutoff tool, a hydraulic pulse tool. As the image on the screen is showing, it could be a torque wrench, it could be a torque screwdriver, it could also be just a static tool without any torque signal at all. so we can do some testing that way. But this is how the system is used to be able to measure the torque in line or on the application. And so how does this work? And so if we look at a typical reaction style transducer, we have a shaft, and on that shaft we have a laminated strain gauge on the shaft, and we basically have an electrified circuit on there. And then as we get torsion on the shaft from the reaction of the torque, the resistance within the electrified circuit is going to change. And so that change allows us to measure the difference between the shaft at rest and then with torsion. And that's how we can develop the torque signal from a reaction style transducer. And so that's a little different from a rotary style transducer. And how that primarily functions is we have a shaft that rotates, and around this shaft we have slip rings, and then we're able to measure those slip rings. And as the shaft is rotated, and we're constantly measuring the resistance between the different rings. And as we get to the shutoff point, we get some deflection in the shaft. And now we're measuring that deflection with the resistance between each of the slip rings. And that's how we can generate that particular signal from an analog to a digital torque reading. So that's how the rotary sensor works. It allows us, again, to be able to test the tool on the application in line and without removing anything other to the application. So what is the accuracy of a rotary sensor? So just like any other torque sensor, it does have an accuracy. If we couple that sensor with a torque analyzer, then we can use what would be the paired or system accuracy. And that's typically for the Mountz analyzer with a sensor. We have a system accuracy of plus or minus 0.5% from 20 to 100% of reading of the full scale of the unit. And that's typical for all of our sensors that we have within our line. If the sensor is purchased by itself, it does have a accuracy of plus or minus 0.2 of full scale. So the difference between of reading and full scale is obviously if we have a full scale reading anywhere up and down the range of the sensor can be plus or minus that 0.2 at the full scale. When we're looking at a accuracy statement that's of reading, then it's wherever the system is reading from, we're plus or minus 0.5% there. So the standards for a rotary transducer are the same again as other transducers. You have the ANSI Z540 and the ISO 17025 certification for those sensors, and they do need to be calibrated on a frequency-based, either 6 months, 12 months, or depending on the usage, how you would like that sensor to be calibrated with your analyzers. So that's how the accuracy works in conjunction with the analyzers of the sensor itself. So when we look at when we can do the measurement of the dynamic torque, there are basically 3 different areas that we can look at. We can obviously measure before the assembly process. So we could set the tool up on a joint simulator and run that tool down. We can do it during the assembly process. And then we can also do it after the assembly process through some auditing. Now, of these 3 particular cases, the most beneficial time is going to be when we're actually doing the assembly process, because the tool is being used on the part. And so we're seeing what's reflected within that particular joint characteristic. The other two scenarios are going to change the value, perhaps, depending on the joint characteristics when we're doing the testing. And so coming up in September, we're going to be doing a whole webinar based off of these three different scenarios. So that's coming up in September. So those are the different stages that we can test from. When we look at our poll question today, we're asking in your process, where are you measuring in the assembly? Are you doing it before, during, or after, or if you're doing all three of these? And so we'll go ahead and give you a minute or so to answer the question, and we'll see what we get. All right, so with our poll ending here, it looks pretty split all the way down the line, where we're getting some before, some during, some after, and then we are getting some that do all three. So kind of a scenario where all three was the winner, but not by much. So anyway, thanks for participating in the poll question for today's subject. So now, what are some of the other uses that we can use with the rotary torque sensor? And one of the big ones is being able to use it for R&D purposes, allowing us to be able to look at a joint that may be problematic, and we can determine whether the torque specification for that particular joint is correct. And so we do have that ability to tighten down the fastener on the application. And when we're looking at developing a torque specification, what you'll do primarily is take that to the yield point of the fastener. So at the point at which the fastener breaks, we can measure that particular torque value. You can do that in torque over angle. You can do it with torque over time. But this helps to develop the point at where the fastener itself eliminate or moves from the elastic to a plastic state. And so if we can keep that clamp load for the fastener in the elastic state, that is going to be the best scenario for that particular fastener. And so when we find that yield point, we can then take a look at the joint characteristics, and we can back that off from that percentage of usually 20 to 30%, maybe 25%, just depends on some other factors, if there are gaskets and things like that. But that is typically where you would start. And so when you are seeing issues or problems with a particular fastener, one question may be to ask, how is that torque specification assigned to the part? Was it done based off of which fastener we're using? Was it done just based off of a formula? If you're using torque equals the coefficient of friction times the distance of the nominal bolt of the tensile force of the fastener. So there are things that we can look at if we're having issues with a particular fastener, and we can do some R&D to see if we need to adjust the torque setting. So a rotary style transducer is excellent for this type of process. If we want to use the rotary sensor for doing auditing or torque verification, this is by far probably the best case scenario for use. We can take a torque sensor out onto the factory floor. We can come to an operation, put the sensor between the tool and the part, go ahead and run that down and take a few readings and make sure that the tool is producing what it is supposed to be doing. And so with that, in conjunction with the torque analyzer, we can save those readings. We can make sure that we're limiting the exposure that we may have from a tool that may be drifting. If a tool is sent out to be recalibrated and it is found out of tolerance, at what point did it go out? What parts might that affect? Is there any type of audit that may need to be done to determine if it is critical that certain components be reworked? So it does allow us to be able to have a purpose when we're verifying it to make sure that the tools are performing as they are supposed to. And so with this, each sensor has its own specific range. So we can test from about 10-inch ounces all the way up to 1,500 foot-pounds. And so there are different models within those different settings. So we could test different tools with different torque settings. But auditing on the factory floor is a really primary use for the rotary style transducer, again, helping us to measure the dynamic torque that's being produced out on the factory floor. There are a few different styles of rotary style transducers. There are brush style transducers. These would be used again for R&D or possible torque verification. We do have brushless models. These would be helpful for use where a sensor is going to be part of a permanent piece of the assembly process. So that torque analyzer, or excuse me, the torque sensor is going to always be present, capturing readings of very critical joint assemblies. So we would use a brushless style transducer. And then we also have angle transducers that basically will signal at every degree of rotation. So they are built with an angle encoder in there. And so we use those with the torque analyzer to do measurements of different torque and angle type of settings. This can also be useful if we are doing auditing where you want to look at testing a fastener after it has been torqued. And so there are a couple different ways that we can do that. One would be the first movement test, where you put your fastener in the forward, or excuse me, the actual fastening rotation, and we move that about 5 degrees, and we can see what that value is. That's going to be a representative of the torque that was applied. You could also do a line test, where you would mark the part and the fastener, break that fastener loose in the loosening position, and then retighten those that fastener to the line on the fastener and the part, and we can see what that value is. That would be representative of the actual torque that was delivered. Now, is it going to be exactly the same? It's not, because the coefficient of friction may change due to a lot of other variables within the materials that are used, how long that different metals may have corroded or contact, things like that. But it's going to be very representative, and it will help you to develop a model of uncertainty that you can verify with those different values to for the auditing process. So that is what we can use the angle or the angle sensor for. So right now we'll go ahead and we'll jump to how we can use this in our demonstration process. And so right now what I have is the torque analyzer. I have a rotary style sensor here. This one has a reading of 5 to 50 inch ounce, or excuse me, 5 to 50 inch pounds. And so I'm using the analyzer here in an automatic clear mode. And we have the system is using a 1/4-inch hex on male on one side and female on the other. And this again allows us to be able to put the tool in between, or excuse me, the sensor in between the tool and our part, and we can go ahead and take some measurements. And so if we look at this with a hand tool, we can do that. So let me go ahead and attach the screwdriver here to the screwdriver, and I can go ahead and take a reading. And now this is giving us a value at 8.9 inch-pounds or so. If I go ahead and run it again, we're now at 8.5. So this gives us that ability to, again, measure what's happening on the thread block here, which could be representative of an application. So this can be done, again, with a hand tool. If we want to do some joint analysis of what's happening with the rundown, we can use the analyzer, which I do have hooked up to my PC, and we can use the software that we have included in the PTT here, and we can do a graph rundown of what is happening with the fastener. So if I go ahead and we can start the rundown, and we'll get a graph of what is happening when the tool cams over. If we're seeing something that's crazy looking like that, then we can see what is happening with the rundown. If we want to save this information, we can do that. If we want to come in and look a little bit closer at what's happening in an area, we can do that as well. Or we can highlight a certain area and see exactly what's happening with that process using the rotary sensor. And so if we want to do this with the dynamic tool or a power tool, we can also do that as well. So I have a power tool here, and we can go ahead and do the same type of testing. Let me go ahead and stop what's happening on the software. And we'll change our mode here back to peak. And so we're measuring the highest peak torque during the rundown. And so let me make sure we have a fastener here that has a little bit of thread going. And so we're measuring right now at just over 26 inch-pounds. And so on. And so again, we can see what's happening with the power tool on your application, giving us that ability to see what is or what may be happening with the tool at a certain time. We have documentation of that. And so we can track that tool and the process over a period of time. And so if we look at what another type of system that we have that can be used as well to demonstrate and look at how we can do some joint analysis, that would be through the use of a transducerized power tool. And so we have a transducer that is built into the tool, and this will allow us to look at a particular rundown of a particular joint that may help, again, looking at a problematic type of application where we're seeing some inconsistencies, we could take a look at the joint characteristics using a transducerized power tool. And so let's go ahead and take a look at what that looks like. Let me just make a few modifications here to the screen that we are seeing. Okay, and so right now I have our ECT software hooked up to one of our DC control tools, which has a built-in transducer in that. And in this case, we can go ahead and we can monitor what happens during the rundown through the use of our graphing function, where we can save these graphs and do some, again, some joint analysis. We do have two different channels that we can review. So on channel 1, we have torque. On channel 2, we have angle. And so if I go ahead and hit start, and we'll go ahead and run these fasteners down, you can see that we are generating a torque curve. Now, this is a pretty straight forward type of joint that we're dealing with. But if we had a special application where we're going to be running the fastener down, and then possible there's some additional angle or turn that's happening to the joint, then we can look at that. And so with the software, we can come in and we can look at any point through the rundown curve here, and we're going to see both our torque and our angle. So our final torque here is, or our peak torque when we did our fastening, it was going to be at 2.27. And then we did some angle turn after that in the reverse direction. But this is an example of how we can use the transducerized DC tool as well to look at different and problematic joints that we may be using. So if you do have that system, you could use it as well to do some type of joint analysis and even some torque specification modifications. So with that, that ends our presentation on measuring the dynamic torque. If we have any questions, we can go ahead and move to our question and answer segment. And let's go ahead and is Chris doing the questions today?
Yes, I am, Dave. All right, Dave, thanks for the presentation. We have a couple questions to kick it off here. The first one was, for the torque verification process, is there a recommended number of rundowns that kind of serves as a benchmark?
Typically, you want to do maybe at least 5. If the tool is not in use at the time, you're going to want to make sure that the tool has been exercised. So you'd want to run that down probably about 5 times before you do your testing, but it could be anywhere from 3 to 5, could be 10. It just determined by your internal processes and QMS and the documentation that you may need to keep, but typically 5 readings would be sufficient on a frequency that can be done either monthly, could be done weekly, could be done daily. We have customers that check their tools once a shift, and so on, depending on the critical nature of the fastening process.
All right, great, Dave. The next question is, can a rotary sensor be used for an air tool as well?
It can. You can certainly use a pneumatic shutoff tool with a rotary sensor. You could use a pneumatic pulse tool or a hydraulic pulse tool with the sensor. The only tool that you would not want to use it on would be an impact wrench. So either a small butterfly impact pneumatic tool, you would not want to use that on there because there's not really any torque control. And then the hammering that that happens could damage the sensor. So you can use it on just about every air tool except for an impact tool.
Okay. Next question, Dave, is can you show an example or explain the typical torque curve or curves when determining the yield point when developing a torque spec for a new joint?
Sure. So if you were to look at a graph of what would happen during the yield point, as the fastener gets torqued, let's see if I can go back to this screen here. And if we look at the, say if we took the curve here of the 2 points, sorry, wrong mouse. So if we were to look at these 2 points here, and instead of the image dropping down, we saw this kind of flatten out. So if this peak, this first peak and this second peak here were kind of matching, and we didn't see the valley, it would be almost like the letter N. That's typically what you would see once the curve starts to flatten out. That's where we see the yield point. And that's where you would see the failure. So just before would be your end of the elastic portion of the fastener that would move into the plastic phase. And then you'd have your yield point at that point. So it would almost, again, look like the letter N, and the top of the N would be your yield point, and or your failure point, depending on how far you took the fastener. If you actually took it to the breaking point, you may see a drop off in torque, but before that, you would see a slight leveling off of the fastener, and then you would see the drop off in torque. So I hope that kind of explains it.
All right. Thanks, Dave. Next question we have is regarding the fastening joint portion of the presentation. Can like thread lock, lubricant, or grease influence the torque output from the power tool to the fastener being tightened? And if so, how do you accommodate that in the fastening rundown design?
So anytime we introduce other components to the rundown, it may change the torque output, or it may not change the torque output, but it could change the clamping force. And so if you were to add thread locker to a particular fastener, that thread locker, depending on where it is, can act as a lubricant during the rundown. And so if you do see signs of fasteners that may be stripping when you are applying thread locker, that is a process where we're reducing the coefficient of friction, and it's allowing more of the bolt or fastener to stretch, because the tool itself is looking for a certain level of resistance to meet the torque value. If we eliminate or diminish some of that resistance, then the fastener can stretch more than it normally would under its normal clamping force. So that would be how thread locker could influence the fastening process. Again, you may want to look at doing some destructive tests. You don't necessarily need a rotary sensor to do a destructive test. You could use a simple dial wrench as well. However, you would get much better resolution, obviously, with an analyzer and a rotary sensor. But you may want to look at, is the amount of torque that's being generated now producing more clamp load or pushing the fastener more towards the yield point than you would like by doing some of that destructive tests.
All right, great. Thanks, Dave. It doesn't look like there's any more questions coming in, so I think we can call it a wrap.
All right. And with that, I want to say thank you very much for joining us today. And again, if you have any questions or you would like to see a demonstration by a local salesperson, we can certainly make that happen as well. So again, thanks so much for joining us. And if you have any questions, feel free to reach out to us through our website at mountztorque.com. All right. Thanks so much, everybody. Have a good day.